We have a circuit like this, 3 microfarad and 6 microfarad are initially in parallel. The switch is closed, this the position of the switch, and then we have 3 in series, and then we have a 12 volt cell here. Our interest is to find the heat evolved when the switch is thrown from 1 to 2. For that we determine the initial state, and what is the initial state? This could be chosen as 0 volt, and this is 12 volt, right? This cell maintains that potential difference. And what is the potential here? And you can see that this is how it works out, right? The two capacitors here are in parallel. This is 9 microfarad, this is replacement, and this is 3 microfarad, that one. This is 0 volt, and this is 12 volt. This is 9 microfarad, replacement for these two. This is the point, this one, right? So this is 0 and 12, this is 9 microfarad, and this is 3 microfarad. And we'll have to split when this is to what? Well, the potential difference will divide in the inverse ratio of capacitance in series combination. In series combination, charge will be same in both, and potential will be in the inverse ratio of capacitances. The inverse ratio is 3:9, that's 1:3, 1:3, right? So one part of 1:3 is 12 into 1 by 4, that's 3 volt. So this will be 3 volt. The potential difference is 9 because this is 0. This is 3 volt potential difference. This is 9 volt potential difference. 12 and 3, that's 9 volt potential difference. This is the initial state, right? When you throw the switch to the other position, this is what you're going to get. This will be 3 microfarad, but that becomes 9 microfarad. So this is what we have here. This is 9 microfarad. This is 3 microfarad. And this is of course 0. This is 12 volt. And now we want potential difference across 3 microfarad capacitor because this is 0. Whatever potential difference you have across 3 microfarad will be the potential here. So 12 divided in the ratio 9:3, that is 3:1, 3:1 of 12. So that will be 3 volt here. Sorry, this will be 9 volt here. 3:1, 3 parts in 4, right? 3 parts in 4, 3:1. So 12 into 3 by 4, 9 volt. So this is what we have. We find that the equivalent capacitance isn't changed, right? So if equivalent capacitance isn't changed, well, energy stored in the system is not changed, isn't it? Energy stored is Q squared by 2 C effective. C effective has not changed by throwing the switch from 1 to 2, so no change in energy. Delta U is 0. So if delta U is 0, well, whatever work that cell has done has been converted to heat. And what is the work done by this cell? Well, when you throw the switch from 1 to 2, the charge from this plate can flow to this plate, and of course there is junction here, some of it will go here. So this is being disconnected and you're connecting this, right? So the only path available for charge here is this. So what do we see here? What is the charge earlier here? This was 3 volt, right? 0 and 3. This is 9 microcoulombs, minus 9 microcoulomb. This is minus 9 microcoulomb. Now then it became 9 volt, right? 9 volt. So this will be 327 minus 27 microcoulomb. Hope you get that. This is the initial state of this plate because we are interested in this plate because charge is flowing from here. No path this way when this switch is thrown that way. And this charge flows through the cell like this. So this minus 9 to minus 27, so 18 microcoulomb must have left that. 18 microcoulomb has flown from this plate to this junction, and some of it goes this way and some of it goes this way. So what is the work done by this cell? Positive charge flowing this way, going away. So cell is driving charge, so to say. Cell drives charge when positive charge goes away from the positive terminal or comes to the negative terminal. It circulates. So 12 volt into 18 microcoulomb, this many microjoule. That's how much? 8 into 36, 8 in 1, so 21, 216 microjoule. Sorry, this should be microjoule. This is the work done. And this is the heat evolved, because no change in potential energy. What is work done? What is heat evolved? Work done minus change in potential energy. This is 0. There is no change in potential energy here. So work done is heat evolved, which is 216 microjoule. You could also have looked at these plates, because charge is coming from here to here. You can look at this also. Well, what is the initial charge here? This was earlier, this situation, right? So this is 6 microfarad and 3 volts. So this is 18 microcoulomb, minus 18 microcoulomb. And this is plus 9 microcoulomb, right? This is a potential difference of this situation, right? Initial state, we're looking at 9 volt, 27 microcoulomb. So this is plus 27 microcoulomb. The charge together on this is 7 microcoulombs, 9 microcoulomb. And what does this change to? When you connect this way, this potential difference become 3 volt. 3 volts, so this will be 9 microcoulomb, 3 into 3, 9 microcoulomb, 3 volt potential difference. This will be 12 and this becomes 9. So this 3 volt potential difference. Same 3 volt potential difference will give us, this will give us 3 into 6, 18 microcoulomb, plus 18 microcoulomb. So what is the change in charge here? This is minus 18 plus 27 earlier, that is plus 9. Now it is plus 27. So 18 microcoulomb must have flown, which is what we got here too, right? Minus 18 and 27. When you disconnect this and don't do anything else, the state will remain the same. But when you disconnected this and reconnected here, the charge in on these two plates will change due to the charge that flows in along this cell path. So this changes the charge from total of minus 18 plus 27, that's plus 9, to plus 27. So 27 microcoulombs has flown in there. That's it. So another way of looking at the charge flown. Anyway, there is no change in potential energy of the system, because effective capacitance is not changing. But as a cell is driving charge, work is done by this cell, and all the work done by it is converted into heat. We have a charged capacitor, capacitance C. It's a parallel plate capacitor, and with a charge Q on its plates. It's been charged by, say, using a cell, and we know the charge on the plates. The gap is D and the area of the plates is A. We want to grab the plates and pull them apart slowly. And as you increase the gap between the plates, the capacitance will decrease. Capacitance of 12 of a parallel plate capacitor is epsilon 0 A by D, right? So if D is increased, capacitance decreases. So our interest is to double the gap between the plates. Now, what is the change in the energy of the system? Since we have decreased the capacitance, there will be a change in energy. Well, you could use Q squared by 2C as the formula for the energy stored in the capacitor, because Q is not going to vary here. We are not connected this to a cell, so Q is not going to vary. And since there is no change in Q, there is no flow of charge anywhere, and there is no heat evolved also. So all work done by you will cause a change in electrostatic potential energy. So what is that work done then? Final potential energy, Q squared by 2C. C would have halved, right, because gap has been doubled. This is C by 2, and minus initial potential energy is Q squared by 2C. This is work done is equal to change in potential energy. And this you can see is going to come to Q squared by 2C. That's it. This is the work done. Alternately, you can do work done calculation just for fun through force and displacement. What you do realize is that the force between the plates of a capacitor is sigma squared by 2 epsilon 0 into A. How do you get that? If this plate is in the field of the other, which is sigma by 2 epsilon 0, and the charge present here is sigma. This is a uniform field due to the other plate except at the edges, which we ignore. Sigma by 2 epsilon 0 into sigma A, that's what we got here. So sigma squared by 2 epsilon 0 into A into, you double the gap, that is you have increased the resistance to move the plate by D. So this is it. And you can express that in terms of Q. What is sigma? Sigma is Q by A, right? This Q by A. This Q squared by A squared. 1A gets cancelled, so 2 epsilon 0 A. So Q squared by 1A gets cancelled into D. And epsilon 0 by D is C, right? This is Q squared by 2C through force and displacement. Yet another interesting thing you can do is you have created an extra volume of A into D, right? You have created an extra volume of A into D, and in that extra volume you have a uniform field of sigma by epsilon 0. In the space between the plates, the field is sigma by epsilon 0, field due to both the plates. If you are interested in force on this plate, you will ask what is the field due to the other plate, not what is the field in the gap. If we want the force, that is sigma by 2 epsilon 0 to sigma A is the force here we said earlier, right? Anyway, the field here is sigma by epsilon 0. The increase in volume is AD. So in that extra space that you created of volume AD, you have now electric field of sigma by epsilon 0. So increase in energy stored there in that space. So that would be like work done would be change in potential energy. You have half epsilon 0 E squared is the energy density in space into the volume has been increased by AD. So the extra volume created is AD, in that the field is E, and E is sigma by epsilon 0. This half epsilon 0 sigma by epsilon 0, sigma squared by epsilon 0 squared AD, epsilon 0 cancels out, 1 sigma is Q and epsilon 0 by D is C. So you get Q squared by 2C here. Interesting ways of arriving at this result. One is simple and straight. Change in potential energy is the work done. No other form of energy is involved here. Agent is moving the plate slowly apart, so no change in kinetic energy. And we're not bothered about mass and gravity and stuff like that. So this is simple. This is through force displacement, regular routine. Force is constant, so things are simple here. Then the change in the energy stored in the space, the volume of the space between the plates is increased from AD to 2AD. So this increased space is this. In that the work done by you, the mechanical energy you spent is stored as electrostatic potential energy in that space. We have a charged capacitor here with capacitance C, and this capacitance C is with the dielectric constant K fully filling the gap. It's already charged. What happens if we slowly pull the dielectric out? If you take it completely out, the capacitance decreases by a factor of K. It will become C by K at the end. So our interest is to find the work done in pulling the dielectric out. And how do you find that? Well, work done is change in potential energy. You don't have to do force displacement ideas anymore. So work done is change in potential energy. Final potential energy is what? Q squared by, charge is not changing here because there is no external connection, no cell to drive charge and maintain potential difference. So here potential difference will decrease. Q squared by 2 Q squared by 2C by K. Capacitance decreases by a factor of K. And this is initial. With the dielectric capacitance was C, now it's K times less. So this is it, Q squared by 2C into K minus 1. We have only air at the end, right? This is it. So in extracting the dielectric out, imagine you're doing that, slowly pulling it out. you are using your biochemical energy and converting that into electrostatic potential energy. So you're producing electrical energy by doing mechanical work at the expense of your biochemical energy.